Hi everyone, my name is Julien, and today I'll be presenting our work on using EGRAPHS for Boolean FHE circuit synthesis. To give a brief outline of the talk, I'll first introduce what fully homomorphic encryption, or FHE, is, and then discuss what FHE circuits are and how they're currently optimized. I'll then discuss our efforts to apply quality saturation towards this problem, and how that led us to our current solution, which we call cut tracing, using EGRAPHS. And then I'll present finally a preliminary evaluation of this method. Fully homomorphic encryption is a privacy-preserving technology that allows computation over encrypted data. Typically, the operations of addition and multiplication are supported. So I can take two messages, which we would call the plain text, and encrypt them, and then on these ciphertexts I can add or multiply them together to get what would be the result of adding or multiplying the plain text values. In this talk, we're particularly interested in the case of those plain text values being Booleans, which we call a Boolean plaintext space. In this setting, additions and multiplications are equivalent to XOR and AND gates respectively, and so we'll use them interchangeably going forward. This case is of special interest because a Boolean plaintext representation is needed to homomorphically evaluate any algorithm that requires a bitwise number representation, such as a CRC32. In addition, using a Boolean plaintext space admits the use of Boolean circuit optimization techniques, which we will discuss further. However, the primary bottleneck of most FHE schemes is the overhead of these homomorphic operations, so for this reason we're interested in how to optimize these computations and reduce the overhead. First though, I will discuss how FHE computation is represented. We say a Boolean FHE circuit is a DAG of XOR and AND gates that compute homomorphically over ciphertexts. This is also called an XOR AND graph, and an example for a full adder circuit is pictured at the right. Our goal is to minimize the time to evaluate the homomorphic computation in this graph. The cost of doing so is primarily dictated by two factors, the multiplicative complexity and the multiplicative depth. Multiplicative complexity, which we abbreviate MC, is the total number of ANDs in the circuit and scales the runtime linearly. Meanwhile, multiplicative depth, or MD, is the maximum number of ANDs in sequence, or the depth of ANDs in the circuit, and causes a quadratic increase in runtime, mainly due to the fact that ANDs in sequence increase so-called noise in a ciphertext, and the ciphertext noise has to be globally increased to ensure that the decryption is still correct. And in turn, that has the effect of making every operation more expensive. Finally, XORs contribute a comparatively insignificant cost, and so are usually ignored for the purposes of optimization. Prior work on Boolean FHE circuit optimization has focused on peephole XAG optimization using so-called cuts, which are subgraphs in a logic network. Formally, a cut C is a set of leaves L and a root V such that every path from V to a primary input passes through at least one leaf, and each leaf is contained in at least one such path. If C has at most k leaves, we say that C is k feasible. So for example, on the left, a 2 feasible cut is highlighted in the graph. To optimize an XAG, first a set of candidate cuts in the graph are identified recursively using an algorithm called cut enumeration, and then for each candidate, some cost-specific algorithm is used to generate or resynthesize an optimized replacement cut. Finally, the replacements are applied greedily, such that only the replacement cut which has the best gain on the current circuit is used. For MC and MD specifically, two main algorithms have been introduced using this method: ESOP balancing and cut rewriting. ESOP balancing expresses cut candidates in an exclusive sum of products form, effectively resynthesizing the cut for a lower MD. And cut rewriting performs a lookup of cut candidates in a database of known MC optimal 6-input XAGs, which are indexed by the truth table of the cut. So if the XAG improves the MC, then it's replaced in the circuit. However, so far the problem of jointly optimizing those two metrics for FHE has not been considered. And so in this work, we seek to address that problem, attempting to optimize for the overall FHE runtime. As a starting point, we consider simply applying both of these two algorithms to minimize both metrics. And I'll show an example to demonstrate why this approach has its limitations, mainly that the algorithms don't really compose well and are prone to get stuck in local minima. The diagram shows the design space of a particular FHE benchmark, a sorting circuit. The y-axis is the multiplicative depth, and the x-axis is the multiplicative complexity. And the black dot shows the unoptimized starting point for this circuit. We start by applying ESOP balancing until convergence, that is, no further optimizations can be made to reduce the MD, which is shown in blue. We see that this also comes at the cost of increasing the MC slightly. Next, we apply MC reduction, and we notice similar behavior. We've improved on MC again, but then stepped back on MD. And actually, at this point, we're stuck on applying any optimizations. We can't apply either optimization to progress anywhere else without making both stats worse. Now, if we instead apply the MC reduction first, we also get to a completely different design. This one actually ends up being the best out of the three in terms of actual FHE evaluation time. But we're stuck even earlier. We cannot progress here with any optimizations. We can kind of see that the order in which these optimizations are applied heavily impacts the exploration of the design space. In other words, there's some sort of phase-up ordering problem here. So in light of these experiments, we consider equality saturation as a means to optimize FHE circuits. We store the XAG in an EGRAPH, like the graph at the right shows. So the two nodes at the root represent the two ways the expression x and y, x or z can be written by factoring it. And then we saturate the EGRAPH using standard Boolean XAG rewriting rules over XOR and, like distributivity, consensus, redundancy, etc. To extract from the EGRAPH, we use a scheme that's intended to represent HE runtime based on the insight that depth scales the cost quicker than complexity because it's quadratic. We select the best MD terms with a heuristic estimation for MC used to break ties. We used heuristics as we observed the EGRAPHs were too large for exact methods like ILP to be viable, but I'll come back to that soon. The result actually is that equality saturation is most often worse than the greedy ESOP and cut rewriting methods that I just showed. I'll give a small example once again to illustrate the problem. On the left, we have the same full ladder XAG that was pictured earlier. It has an MC of 2, so there are 2 AND gates. Since this is a small circuit, we know it's MC optimal implementation, which happens to be 1 AND gate, and that circuit is pictured at the right. So we'll try to use equality saturation to optimize the left circuit and find, hopefully, the optimal solution. After just 2 iterations of saturation in egg, the size of the EGRAPH has already grown considerably. And despite that, we still observe an extracted MC of only 2. It's worth noting here that we're actually using ILP because the circuit is small enough. So in other words, the MC of 2 is the best implementation present in this EGRAPH. It takes until 5 iterations until we get the optimal MC of 1 from the EGRAPH. At this point, the EGRAPH has exploded to contain 99 E-classes and 394 E-nodes. And as you may be able to guess, most of these nodes are in some sense unnecessary. The majority of them are doing some kind of restructuring, like applying associativity or commutativity, but not actually improving the best circuit in the EGRAPH. On the other hand, consider the process taken by cut rewriting, one of the algorithms to improve MC to optimize this circuit. The circuit is small enough that it appears in the database of 6 input functions, so in just one step, cut rewriting can find the optimal solution. A typical FHE circuit has thousands of nodes, and at that level, this gap in efficiency becomes a much larger problem and causes equality saturation to generally scale poorly compared to the traditional techniques. So to summarize our observations on real benchmarks, equality saturation can explore a wider breadth of designs, but generally achieves a poor depth. So it's harder to find a solution requiring a long series of rewrites. And in addition, the amount of extra nodes generated by equality saturation means that extraction methods that accurately reflect the cost of shared terms, which we would want to reduce the multiplicative complexity, actually can't run. So we're forced to use heuristic methods, which degrades the results we get for MC. One strategy we can use to help is to use coarser rewrite rules that instead of manipulating individual expressions like with distributivity, we can replace larger chunks of the circuit at a time. For example, the rule is synthesized by a prior work on rewriting FHE circuits to reduce multiplicative depth. That strategy helps the first point, but we still have the problem of there's too many nodes in the EGRAPH, just based on the fact that equality saturation more or less applies rules blindly. So based on these observations, we ask the question, can we saturate the EGRAPH with fewer, in some sense, higher quality candidates? That brings us to cut tracing. We observe that the classical optimization algorithms like ESOP balancing and cut rewriting already work on the principle of peephole optimization through rewriting parts of the graph, only that the rewrites are dynamic in some sense, so we can't just directly put them into equality saturation. But we can record the equivalence between a cut candidate and its replaced root in the EGRAPH. The diagram at the right sort of shows this process. An algorithm may identify the red cut as a replacement for the blue, while in the EGRAPH we would just simply record this information instead of destroying the blue and we would just put the roots of the two cuts in the same E-class. So in cut tracing, we simply record all or some of the candidates that are generated by an algorithm like ESOP balancing or cut rewriting, even those that aren't the best candidate locally. And then at the final step, we can leverage standard EGRAPH extraction to extract the optimal term. Of course, the caveat here is that there is no E-matching. All we're doing here is simply remembering every design choice generated by the algorithm. So in some sense, we're still constrained to the design path taken by the original algorithm. We can't exactly deviate by applying something else to the EGRAPH. Surprisingly though, in spite of this, tracing can still identify some sizable optimizations. To further elucidate how cut tracing is used, we present our flow. We apply the same combination of cut rewriting and ESOP balancing, each until convergence, and this flow produces our baseline. Meanwhile, we modify these algorithms to also record every replacement candidate identified in the EGRAPH. Then at the final step, we extract this candidate using some FHE evaluation-oriented algorithm. In fact, actually for this, we're able to use ILP again. Since we have so much fewer candidates in the EGRAPH, we can even add constraints to the ILP formulation, which normally would just take the optimal MC term. We can also tell it to filter MD so that we end up with a solution that's optimal in both. In other words, we're able to extract the optimal MD and MC term from the EGRAPH and then get the optimal circuit runtime from the EGRAPH. We evaluate our flow against the baseline circuit in two scenarios. First, we apply MC reduction with cut rewriting, then MD reduction with ESOP balancing, and the second, we try the other order. The table shows the speedup in the homomorphic evaluation runtime of the cut tracing over the baseline on a suite of benchmarks. And the second ordering is in parentheses, so MD, then MC is in parentheses. We can see that in the best cases for the first order, which happens to be the better overall for the baseline, cut tracing can yield up to a 40% speedup. Overall, we get around a 10% speedup. We can also see that even though there is often an improvement, the results are still quite heavily dependent on the order, which is to be expected from the fact that we're not really deviating from the path chosen by the algorithm. Also, in some cases, cut tracing yields a worse result. With optimal extraction, this shouldn't be the case because it should simply find the same solution used by the baseline. But the issue that we suspect is that the extraction is still not optimal because of cycles that can be introduced, and this is a typical problem for ILP. We notice that what happens usually is that the algorithm introduces some replacement cut, which is a subgraph of the original, and so then there's a cycle that appears in the EGRAPH. This is an active area of improvement for the tool, and we're investigating how we can reduce cycles in the EGRAPH. We also highlight the B-sort circuit, which we showed the design space of earlier. With cut tracing, we're able to find a design that's better than both of the paths taken. It makes a very small compromise in the MC as compared to the MC first path, which was the old best solution, while having the same MD of the other path. So overall better than both, more or less. Finally, we also test cut tracing versus normal equality saturation. For this experiment, we use the synthesized FHE circuit rewrite rules, which I mentioned prior, with the greedy extraction method we also highlighted earlier. The full benchmark suite is not shown here, but we can see that not only does cut tracing provide a 30% overall improvement compared to equality saturation, with, in the best case, a 2x improvement, but even the baseline of simply combining ESOP balancing and cut rewriting also provides a 20% improvement. So equality saturation ends up being worse than just the baseline. And in general, that mainly comes from the fact that we are forced to use a suboptimal extraction instead of ILP here, which won't actually accurately estimate MC. And so then even the baseline finds an improvement because of this. So to conclude, we wanted to optimize Boolean FHE circuits for their overall runtime, which is some combination of MD and MC, instead of just one at a time. So for this, we proposed cut tracing, which is a method that uses EGRAPHs to expand the design space explored by traditional optimization algorithms. In this sense, it's a small step towards combining classical optimization techniques with equality saturation. We saw that it improves sensitivity to the ordering of the passes, though it's limited due to not using the EGRAPH in the optimization process itself. We are interested to investigate how to integrate e-matching and incorporate the eGraph better into this flow so that we can reap more of the traditional advantages of equality saturation. Of course, we would also like to maintain a small enough eGraph so that we can keep using this optimal extraction, which we saw was important for the application. And as mentioned, we also faced issues with cycles in the extraction, which is an active area of improvement. Our code and preprint is available at the link in the QR code. Thank you for your attention, and I will take any questions.
Okay. Yeah. And again, I just want to reiterate, please, hop into the Discord and feel free to ask the authors. I believe some of them may be online at this very moment. Yeah, please go ahead and do that. And then let's go ahead and get the next speaker to go ahead and step up. Okay. Oh, okay, fantastic. The speaker is actually live on Discord, so if there are questions, let's go ahead and take those, and we can get answers in real time.
Hey, can you hear me? My audio is working.
Okay, I'll go ahead and start us off with a question. Thanks for the really great talk. I'm noticing a similarity between the method here of acknowledging that rewrites are not the right methodology to accomplish some transformation, and sort of instead you want to do something outside the eGraph and then sort of record the results back in the eGraph. This reminds me of the trick that many folks have done for substitution and beta reduction when like optimizing a lambda calculus. It's really slow to do that explicitly, but you can sort of just extract a term and then do whatever you wanted to do with it and then put the result back in. And the nice thing about, at least in that setting, is you could sort of just do that, ad nauseum, right? There's no limit to doing that. So is that something you considered for your approach? Like, at least from what I understood of your flow, it sounded like you were sort of limited in the number of steps you could take, but could you just keep pulling eGraphs out and then doing the cut algorithm and then putting them back in over and over again? Would that potentially be helpful?
Yeah, I think there definitely is some similarity in what you're proposing. I think let's see. I think maybe the difference is that with something like beta reduction is with like the example you gave that I understand it, is that you're sort of applying like that the rewrite you're doing is moving in the direction you want in the eGraph, and so you would sort of like to apply that in a way that doesn't add more e-classes in the eGraph. And so what we're doing, I think, morally achieves the same thing, although it exists completely outside of the eGraph. So you do, with our method, like you do run into a wall where like you may not get any better circuit, because you would like once you run this enough times, you may not get any more improvements as well. Like you could still hit like some kind of local minimum because you're still in that same design path of the original. But I believe, yeah, it is a very similar technique. Yeah. Thanks for the question.
Yeah, I'll follow up on offline with that. Do we have any further questions for the speaker? Okay. We have maybe time for one more.
Hi, thanks for the great talk. Can you explain what is like the fundamental difference between the cut tracing and just a rewrite? Like you were recording equivalences in the eGraph. Like why could it not just be like a big rewrite? Like what is fundamentally different between doing that and rewriting?
Yeah, I think the two key differences are with these algorithms, you take like your right-hand side of your rewrite rule is generated dynamically based on what the left-hand side is, and you're also matching. It is matched structurally in the graph to begin with. Like the cut enumeration is also a structural enumeration, but in order to achieve the same thing, if you were to apply it to an eGraph, like with a rewrite rule, you would want something that matches over the truth table of like identified cut to get that right hand side, and not just the structure. So like it is fundamentally different than having like a static set of rewriting rules in like at the start of your program that you then saturate your egraph with. But it could be the same thing as like, yes, having some rewrite rules that if you can dynamically generate if you have an e-matching procedure that can give you if you have an e-matching procedure that gives you like the left-hand side, or you have your left-hand side and you can run some function that optimizes that and then place that in the egraph, then it would be the same thing as that. So it is sort of just that the rule is dynamic in some sense.
Okay, and with that, let's thank the speaker again and switch over to the next presentation.